From black holes that hide in the darkness to the supernova that outshines stars in our night sky, space is always full of surprises. Recently, there's been a lot happening, and we have brought to you two of those hot off the press stories. Welcome to Science Today, where we present to you the latest news and research within science and technology. Astronomers report that an ultra-rare cosmic object was just detected in our galaxy, the Milky Way. Pulsars are mostly neutron stars that rotate at a crazy speed, emitting electromagnetic radiation from their poles. A neutron star is formed when a star that is a few times more massive than our Sun dies, leaving its core exposed. Here, the neutron star will preserve the angular momentum of its parent star, but with a great reduction in its radii. Hence, its moment of inertia is enormously reduced, which lets the star spin at greater speed than it had before. The first pulsar was detected in 1967. Though we happened to be in its plane of emission for long, it was the first time we noticed it when looking out for something, and it appeared like it was pulsing its radio waves once every 1.337 seconds. The time interval between their pulses is so precise that they can be used as a GPS to navigate through space. We have been studying it for more than 50 years, and yet we don't know much about the mechanism behind their beams. So far, we have been able to detect more than 2,000 pulsars with our instruments. Some of them may not be visible as long as their beams don't pass through us. When we are yet to understand something that has been known to us for a long time, even when it was available in thousands, what about an object of which only a very few have been known? The discovery, named MAXI J1816-195, is a pulsar that falls under the category of accreting X-ray millisecond pulsars. Millisecond pulsars are those which spin for a period of fewer than 10 milliseconds. The theory behind their formation is that they are most probably old neutron stars that had weakened magnetic fields and reduced spin rates, but the accretion of matter from their nearby star has increased their rotational speed. At the same time, the presence of accretion supposedly weakened the magnetic field down to 10,000 times less than an average pulsar. So far, only about 18 such accreting millisecond X-ray pulsars have been known. This recent discovery could add some valuable information to our understanding of them. It was the Japanese Space Agency's Monitor of All-Sky X-ray Image Instrument, known as MAXI, that detected the X-ray emanated from the pulsar on June 7, 2022. Soon after this, they posted a notice to the Astronomers Telegram, reporting what they had found and that it was located in the galactic plane between the constellations Sagittarius, Scutum, and Serpens, at the same time encouraging other astronomers to look into the source that produced it. Initially, the astrophysicists from Pennsylvania State University jumped in with the Neil Gehrels Swift Observatory and confirmed the existence of the object. They were able to observe it in X-ray, but not in optical or ultraviolet, and went on to say, this location does not lie at the location of any known catalogued X-ray source. Therefore, we agree that this is a new transient source, MAXI J1816-195. In addition, archival observations by Swift/XRT of this region taken in 2017, June 2022, do not reveal any point source at this location, J.A. Kenney, PSU. It was only after NASA stepped in that things came to light. The Neutron Star Interior Composition Explorer, known as NISA, is a space telescope mounted on the ISS, just like MAXI, but capable of time-tagging X-ray photons with an accuracy of 300 nanoseconds. When pointed at the source, NISA picked up X-ray pulsations at a frequency of 528.6 Hz, which would mean that it takes a meager 1.9 milliseconds for the star to go around its axis once. They also observed a thermonuclear burst, which was likely the result of material accumulated by its companion star. Over time, a pulsar's spin slows down, which in turn reduces their pulsating mechanism, and they stop pulsating after some point. This turnoff occurs over a period of 10 to 100 million years, which implies that the majority of neutron stars that were born before the last 200 million years no longer pulsate. Therefore, the discovery of such a rare breed of pulsar is eminent to learn more about them. Our next story is about the meteoroids that hit our James Webb Telescope between the 23rd and 25th of May, which ended up damaging its mirrors. The James Webb Space Telescope is a flagship program of NASA's Astrophysics Division, like its Hubble Space Telescope, Chandra X-ray Observatory, Compton Gamma Ray Observatory, etc. These programs are carried out at a cost of billions of dollars and specific objectives in mind. The James Webb is designed to study the early stars and galaxies of our universe by tapping into the infrared part of the spectrum. Its primary mirror consists of 18 hexagonal segments made of gold-plated beryllium. These mirrors give the telescope a light collecting area of 25 square meters. That's almost 6 times that of Hubble. As it would be observing in longer wavelengths of visible light to mid-infrared, the telescope has to be kept in a cold environment of temperatures below 50 kelvins, so that heat from the surroundings doesn't interfere with its readings. James Webb is stationed at the L2 Lagrange point that is situated in line with the Earth and the Sun. If you could look at it, you would find it orbiting an empty point in space, as if it is hula hooping all along its orbit, unlike most of the satellites that go around the Earth. This is because Lagrange points are the locations in space where the gravitational pulls of Earth and the Sun give the necessary centripetal force for the object to move along its orbit. Of the available 5 Lagrange points, we have chosen L2 because it is behind the Earth at a distance of about 1.5 million kilometers, which is just right for James Webb to shield itself from the heat produced by the Sun in addition to those produced by our Earth and the Moon. A point that can naturally keep a spacecraft in orbit is also likely to attract other objects that wander in space. This makes it a hotspot for various dust particles and micrometeoroids. Points like these exist for all major bodies in our solar system. For example, Jupiter, which is known to protect the Earth from a lot of meteoroid impacts, has a swarm of dust and rocks whirling around at its Lagrange point. Since we knew all this already, engineers had anticipated that something like this could happen if they were to put a telescope out there. James Webb comes with tiny motors known as actuators that are capable of moving its mirrors. It has about 132 actuators for its primary and secondary mirrors that can change the alignment of the array and give us a better focused picture of what we observe. This feature enables the telescope to withstand all the impacts without affecting its observation. Using these actuators, the damaged mirrors can be adjusted in such a manner that the distortion produced by the damage can be cancelled out. We have put the telescope in a location that is free from debris and far away from the Earth's orbit, so we can't go up often to repair the damage, as we did with the Hubble Space Telescope, which underwent 5 servicing until 2009. Meanwhile, Webb's damaged mirror, C3, has already been corrected by the engineers, and these corrections will be made further until they fine-tune the telescope to suit their needs and get rid of distortions produced by such impacts. Though Webb is designed to last for a minimum of 5.5 years, it is likely to function beyond 10 years, so we don't have to worry about our flagship telescope taking a hit occasionally. Well, when it comes to exploration, as the saying goes, no pain, no gain. Thank you for watching. We'll be back soon with more exciting content. If possible, give us a like and subscribe to the channel. Also, don't forget to put your thoughts in the comments.